Hey class, I am going to go over 6.6 notes with you all. So here is the start. So 6.6 is all about making a binomial distribution into normal using an approximation. So we're going to look back at 5.2 notes, which dealt with binomial probability distribution, and then recall everything that was introduced. So you can go ahead and pause this and write that down. Okay, so now let's talk about N is your number of trials. P is probability of success in one trial, and Q is probability of failure in one trial, or 1 minus P. X is the number of successes among the N trials, and that is what you're trying to find the probability of. Okay, so there are a couple of things that you have to check whenever you change a binomial distribution to normal. So if binomial probability distribution satisfies the requirements that N times P is greater than or equal to 5, and N times Q is greater than or equal to 5, then that binomial probability distribution can be approximated by the normal distribution with these parameters, where you have that the mean is N times P, and the standard deviation is square root of N times P times Q. Move a couple things out of the way. All right, so here is how we are going to use binomial distribution and make it into a normal distribution, approximate it to be normal. So you want to go ahead and write those 5 steps down, and then we'll take a look at it together. So step 1 is you're going to check that NP is greater than or equal to 5 and NQ is greater than or equal to 5. Then you're going to find the mu and then the, sigma? No. Theta? I can't remember my signs right now. We wrote it down somewhere. And then number 3 is change discrete values of x. So remember, x is what we're trying to find the probability of x. We're going to change x into an interval. The interval is going to change it to x minus 0.5 and x plus 0.5. Then you're going to draw your normal curve with the mu, and then with x being 2 spots, and you're going to pick the one that is what I'm going to explain in the next page. And then you'll find the probability by finding your z-score, or you can use the calculator. Okay. Do your z-score and then find your area. Then find probability. Okay. So that's your final step because you're finding the probability. So we need to talk about why we change x to x plus 0.5 and x minus 0.5. The reason is because we're approximating normal with the binomial distribution being discrete, but then we're approximating it with the normal distribution, which is continuous. So we have to change it. So binomial distribution is discrete, and we are changing it, approximating with the normal probability distribution, which is continuous. We have to compensate for this change. And so we are going to use the continuity correction, which is change x to the interval of x minus 0.5 and x plus 0.5. Just trying to move things around. Everything's tight over here. Okay, so how to show the interval on the normal distribution. So let's say we're finding probability is exactly x. So to find probability that x equals x, whatever x is. So in this case, we are going to say that x is 122. So then our interval, this is our interval, in x minus 0.5. This is your interval. Draw the normal curve with mu, then draw a vertical stripe area centered on x. Mark the left side with the x minus 0.5 and the right side with x plus 0.5. So if our x is 122, we're finding out when x actually equals 122. Then we'll do an interval. We're going to say 122 plus half and 122 minus half. So then we get this interval of the 121.5 and 122.5, which makes this vertical stripe area. And that's what we would find when we want probability that x actually equals x. It's not just a line anymore. We're actually doing an interval between plus 0.5 and minus 0.5. So this interval is going to also change when we find out, when we're trying to find the probability is less than x, greater than x, less than or equal to x, and greater than or equal to x. So that's on the next page we have here. Notice my normal distribution curves are not the same every time, but that's okay. So here's your probabilities, and here's the statement that goes with it. And this is your normal distribution, what it's going to look like, and what area you're actually finding. So if we're doing probability that x is greater than or equal to 120, that's at least 122, that's at least 122. So we're actually going to do this 121.5, and we're going to find the z-score for that, and then find that area. Then whenever x is just greater than 122, that's more than 122, we're actually going to go to the top of the interval. Instead of being at the bottom because it says at least, this says more than, so it doesn't include the 122. So you're actually going above it using that interval that we use, the plus 0.5. And then when we do x is less than or equal to 122, we're talking about at most. Since it says less than or equal to, we're going to go to the far most interval, which is our greatest number, 122.5, and then we're going to do at most, so it has to be, this is the most we can have, so we're finding the area to the left. And then when we don't have the or equal to, this says fewer than 122, we're going to go to the leftmost because it's not actually including 122. We're going to use our lower interval. And then I forgot to put whenever x actually equals 122. So I'm going to put exactly, that was on my last page, but to have it all on one page would probably be good. Exactly 122. This is whenever you'll do the 121.5 and 122.5. You're finding the area of this. Okay. So hopefully that makes sense. So you're going to have to look back at this chart as you're going through problems to make sure you're using the right x value. Is it the plus 0.5? That's when we're talking about being at least and more than, or is it using the minus 0.5 and, these are the minus 0.5, sorry. It's at least and fewer than, and then these are 122.5, you're using the upper when we do more than and at most. So this or equal to sign, that's what tells you to use the bottom one for this one. And then just greater than, it's going to be the top. Then or equal to, you're going to include the rightmost, the greater than. Okay. All right, so let's look at example 1. This is in your textbook. So if you want to look at your textbook, this is on page, let's see, 285. Okay, so looking at 285, in one of, I guess I can show y'all what it is. In one of Mendel's famous hybridization experiments, he expected that among 580 offspring peas, 145 of them, or 25%, would be yellow. But he actually got 152 yellow peas. Assuming that Mendel's rate of 25% is correct, find the probability of getting 152 or more peas by random chance. That is, n equals 580 and p equals 0.25. Find p at least 182 yellow peas, or 152 yellow peas. Is 152 yellow peas significantly high? Okay, so let's write down what we need from this. So n was 580. X is going to be at least 152. And then P is 0.25. So Q is 0.75 because P and Q have to add up to 1. Check the requirement. So let's do N times P. So that'd be 580 times 0.25. And then N times Q, 580 times 0.75. And I think that's going to be greater than 5. 580 times 0.25 is 145. And then 580 times 0.75 is 435. Okay, so this is satisfied and this is satisfied. So both requirements are good. So let's find mu. Well, mu is N times P, which is that. So mu equals 145. And then our standard deviation is square root of 580 times 0.25 times 0.75. 580 times 0.25 times 0.75. Take the square root of that. And that is 10.4. Well, 4283. Okay, so let's do our correction for continuity. So we are going to do X, which is at least 152. So we're going to do 152.5 and 151.5. So this is our interval. Draw normal distribution. Okay, so we want at least. So let's see. If I look back here, at least is this one right here. So we're doing the area to the right. So I'm going to do probability that X at least, so that'd be greater than or equal to 152. And so we're looking at the area to the right. So let's draw our normal curve. Okay, so this would be 145 is mu. And then 151.5 and 152.5. And it says at least. So that means we're going to include the left interval. So the lower interval. So it's going to be here and then shade to the left. Okay, so use a calculator to find the area, or you can do your z-score and use the table. So let's see. We are going to do our table. Not table. We're going to do the normal PDF. So our lower would be the 151.5. Upper goes on and on forever. Mu is 145. And then we have 10.4283. Okay. So the area, so the probability that X is greater than or equal to 152 is 0.2665. So it's about 1/4, 25%. Okay, so is that significant? So remember, significant means if it was 0.05, but it's not. So let's look at the interpretation. So the result of 152 is greater than 154. He expected with his theory. So we see it's not significantly high. That is a result that can easily occur with a true rate of 25% of yellow peas. This experiment does not contradict his theory. Okay, so let's look and see what other examples we can do. So let's talk about using the same information. Oh, sorry. Let's find the probability that X equals exactly, what was it, 152? So whenever it's exactly, we're going to use the same information. So this is 151.5, 152.5. So it's this area right here. So we are going to use the calculator again. So we're going to do the normal CDF. And my lower is 151.5 and my upper is going to be 152.5. And then the same thing on standard deviation and the mean. So that probability equals 0.0305. Okay, so the probability of getting exactly that is about a 3% chance. So it says, we saw that X successes among N trials is significantly high if the probability of X or more successes is unlikely with a probability of 0.5 or less. In determining if being exactly 152, we need to look at that at least instead of looking at exactly. But this is how you'd find the probability of getting exactly 0.035. All right, so that is it for the notes. Go ahead and start the assignment. I'm going to look through the assignment and see if there's anything I need to explain further, and then I'll post that too. All right, see y'all.